Hello, this short movie will discuss a problem or a method of desmearing the data which would come from, for example, a USAXS instrument, USANS, which is ultra small angle neutron scattering instrument. There are some other slit smeared geometries in small angle scattering, so this is not necessarily a very common problem, but it is not unusual. So here in front of me we're looking at an Igor Pro, and in here we see a image. So this would be a image. I called it isotropic image because the data in the image are from an isotropic scatter. One of the problems you have in slit smeared data is that really the mathematics of the slit smearing desmearing procedure work really well only for isotropic scatters. If there is an isotropy, in this type of image, you basically cannot desmear the data, surely not with the tools which Irena contains. Now, what is slit smearing? This is the first thing which you need to understand. So, if this would be small angle scattering data, and you're looking on an intensity, there's a somewhere here in the center is a beam center. There's a beam stop covering the beam center, and there's the stick which typically holds the beam stop in place. There are some artifacts here which I didn't bother about removing or anything. And now, if for standard modeling methods like the Irena, the input data are really an intensity along a arbitrary line which goes from the center towards outside. If the sample is isotropic, that line can be in any direction, it doesn't matter. And really what you want is the intensity along this very, very narrow line. And of course, since these are pixel detectors, so they have a pixel size, you could think about that you're looking on one column or a row of points, and you're basically looking on how the intensity changes with an angle. So that is what a standard, what's called pinhole collimated data are. Now, in case you have slit smeared instrument, the instrument does not measure one pixel at a time. And what it does, let me just zoom in place. Just zoom in place and zoom in and zoom in. So if you look on that on here, in this case we would be looking, for example, along this line going up, and we'll be looking at one pixel and second pixel and third pixel and so on. And that's a pinhole data. However, in case of slit smeared instruments, these instruments collect multiple pixels perpendicular to the data at the same time. So you can imagine that in order to measure the data, the slit smeared instrument will measure a line of these pixels. It would cover, let me just zoom in even more so it's more obvious. It will measure not only one pixel at a time, but it may measure a multiple pixels, for example, like these. And so at the moment when you're looking on this specific Q, a distance from the center, we're looking on this angle here, instead of getting a intensity from one pixel, which is at that distance, you're actually getting intensity from this one pixel, but also from pixels which are at slightly higher angles, because you can imagine the pixel here has a slightly higher distance. So the distance of this pixel to the center is something. The distance of this pixel to the center is actually something bigger. And so basically you can think about slit smearing at any Q which we are measuring. It actually measures not only that Q, but it integrates over a slightly larger range of Qs. And how far in Q it integrates depends on what is what's called slit length. In other words, this distance from this straight line towards the maximum angle which it collects here to the maximum pixel here, it is called what's called slit length. It is expressed in Q units, and it's typically fixed for a given instrument. And then basically that is what is used for smearing of the data. So it's kind of a rolling average. Now, what is its impact and how do we remove it? So if you look here, the Irena does have in support tools something called desmearing. Okay, so if you pick a desmearing package, and then I'm gonna pick a USAXS data, there are a few data sets which I collected. I'm gonna graph them. Here is a data set which now I want to desmear. It starts somewhere at the minimum Q. Keep in mind, when I collected this point, I have collected not only intensity in this point, but an intensity at this point and at higher Q. So I'm running a rolling average. Notice this is a log Q intensity. Now the instrument has a slit length. Slit length is a number expressed in Q units. There are infinite slit length instruments. That means that this number is much higher than its maximum Q value which it measures. In my case, the USAXS instrument measures up to about 1 or in this case even 2 inverse angstroms, and the slit length is 0.027. So with that, this is not an infinite slit length instrument. So now, how do we desmear these data? There's a procedure here. What you do is you load in the desmearing panel. You don't have to worry about too much if you have USAXS data, because you just check the checkbox USAXS, pick the folder with the data. It will fill in here that you have the slit smear Q, intensity, and error. When you hit the graph, it will create the graph here. It will also pull out the slit length. If you are trying to desmear data from a different instrument, you will have to provide the slit length yourself. And again, it's expressed in Q units. The first thing which you want to do in this case is you want to go in and remove any noisy or bad points at low Q or at high Q. In this case, I will trim the data somewhere here and just remove it, even though I'm going to leave this. Let's do this. I'll just remove them all the way here. I'm going to remove all of this fun stuff. Now, actually, if you think about that, it's a rolling average of 0.03 inverse angstroms. Turns out if you go that's expressed in Qs, it's about here. So the slit length is about in this place. That's about the place where the slit length is, which is slightly higher. It's about here. It's about here. That's about where it is. Okay, so any data below here are slit smeared, so there's a significant impact of the slit smearing because you are averaging data at higher Qs. But actually, when you are at 0.2 inverse angstroms, the slit length is like at about 10% of it, and there's basically very little effect on the data. So the USAXS instrument at the APS has an advantage that we can actually get from a heavily slit smeared range, which is here, to a basically pinhole collimated range here, and we can prove that we can actually measure data on a pinhole SAXS instrument. There is very little to no effect here. I'm going to remove the data at this point. There's some diffraction peaks which are effectively pinhole collimated. We don't actually care about them too much in this case. I'm just going to remove the data. So I'm going to be dealing only with the data in this Q range. We are going from over a very heavily slit smeared range through a medium slit smeared range to basically pinhole collimated data in our case. Now, as I said, you can trim the data, you can select it with cursor. So if you decide you don't want the first point, you just trim the first point away. You also trim away the high Q points. And what you want to do is remove any noisy, any bad data. In this case, basically make sure that you're looking only on robust, trustworthy data, which you want to desmear. If you happen to have one point, sometimes you have one point which sticks out. If you put a cursor A, which is the rounded cursor, over that point, you can remove the single point from the middle of the scan. So it's possible to basically clean up any accidental garbage points. I strongly discourage people from using smoothing. That data should never be smooth, but sometimes they are so noisy that it basically is required. There's a whole smoothing function here. We don't need to do it really not with these data. The next step is, which we have to do, and I'm going to shrink this a little bit smaller, we have to extrapolate data. In order for the code to desmear the data, it has to be able to slit smear them. However, in order to slit smear them, it has to know how the data look like beyond when it actually has the data in this case. So what we can do is we can select the range. The green range will be used for extrapolation, and we need to select a proper function which will extrapolate that correctly. Most typically, if you have data which are falling as some kind of power law slope, maybe Poirot slope, maybe not necessarily exactly Poirot slope, and then have some background, flat background component, the power law with flat works best. Sometimes you need to use power law if there is very little to no background, and sometimes you just have to drag around the cursor. You can see as you drag the cursor around, the green color will change and the fits will change. So this basically now, this black dotted or blue dotted curve, and now it generates these few new points. And since the data go to 0.2, 0.3, 0.4, 0.5, we know that we need only very few data points in there. If you start getting numerical errors because it produces a negative extrapolation for intensity, which is not physically meaningful, you have to change different range, or you have to change a different function. When you go to desmearing, there is a number of choices here. I suggest you read the manual for understanding them. Suffice to say, most people will be happy with using a fast method. And then typically you would do 5 to 10 iterations. I'm just going to do 5 iterations. This is a simple system. Now what happened here is the code has done 5 iterations and it generated new data sets. So now let's explain this curve here. The black curve are the slit smear, that's the input data. You can see that's this curve here. The red curve is the current desmeared fit. In other words, that's the data which when they are slit smeared would produce this. So this is actually, the red curve is our result. When do we end and how do we know we are done? That's what this standardized residual is telling us. So this dotted line is +1 and -1. The rounded circles are normalized residuals, and what you want to achieve is use the minimum number of iterations needed to put these dotted circles mostly between plus and -1. If you have here and there 1 or 2 points above and beyond, it doesn't matter. Remember, these normalized residuals are calculated also based on uncertainties for the points, and if the uncertainty is not very good, then these points, this may not be even achievable. But anyway, what you can see is, in this case, of course, there's no effect on the curve here at high angles, so there is no change, so there is no normalized residual. Then in this case we have some noise in the data, and you can actually see that the points are kind of jumpy around here, so you get a bigger problem, but that's okay as long as those points are, you know, kind of symmetric around 0. We're okay with that. And then we have a curve going to lower Qs. There's clearly a little misfit here where most of the data are below. We can do maybe one more iteration. When you do one more iteration, you can see this thing actually gets much closer, and we can do it one more. And what you achieve is a curve. Now the red plus red curve here is the result, is the desmeared data. That's a desmeared equivalent. That's the data you would measure on an area detector if you were using a pinhole type instrument, and it's the intensity along that line from the center going all the way out. Whereas the black curve is the input data set. When you are happy with that, you can simply hit save data, and it will create a version of data which is DSM Q intensity and error, which is now going to be used. Now, various other choices here may be useful. Once in a while, you should use a minimum reasonable number of iterations. As you keep going and monitoring more and more and more, what you are effectively doing, you're increasing the noise in the output data set. You are not really improving too much, you're just increasing, because you're trying to fit with the desmear data, you're trying to fit any noise on the input data, so just don't overdo it. Here's actually a nice example of why the slit smeared instruments are so useful. If you look at that, the input data set had a dynamic range of 10 to minus 2 to about 10 to the 6 and a half, 10 to the 7. So actually the input data set had a dynamic range of intensity of about 9 decades. That's what our USAXS instrument combined with SAXS instrument can do, and that's necessary because it measures 1, 2, 3, 4, about 4 decades in sizes. So if you look on that, you actually have to have a big dynamic range in intensities. However, at the end of the day, the pinhole equivalent which you use for modeling, this is what you model with. Even if Irena uses directly slit smear data, you are fitting to actually that red curve because it has a slit smearing built in. Actually has about 1.5 to 2 decades more. So actually at the end of the day, the slit smeared instruments are equivalent to a pinhole instrument with even much higher dynamic range of intensities, which would be really difficult to achieve with current existing detector technology. So this is it. We basically created a nicely fit data set. I'm just going to repeat one more. So I'm going to go in and I'm going to pick maybe an example, and I'm going to do it again. So I pick the sample, I pick the USAXS, I pick the sample, I'm going to do graph. When you do that, it returns you back to the first tab. What I want to do next is I want to take the square cursor and remove the points. I'm not going to be bothered about these guys. I'm going to do a trim on that. Now notice I still have some points here which are going to be a problem. So in this case, what I want to do is I want to take the rounded cursor, put the rounded cursor over a point I want to remove, and hit a button. Oh, and it wants me to remove this cursor away. That's a protection, that's a safety feature. So I'm going to remove that. I'm so going to remove this one. I'm going to remove that one. So you can see I'm slowly cleaning away the noise. These specific points were created when I was merging together USAXS and SAXS, and then there is an overlap region in which the higher noise instrument may actually create these type of points. So after this, and I can also go here and maybe remove this one. That's a diffraction peak in the sample. It actually probably should stay there, but for the purpose of desmearing, I'm just going to remove that. Okay, so now I have that. I can go to extrapolate, and when I go to extrapolate, you can see it's nicely extrapolated. All the points were removed. If you decide you want to remove more, you can actually go back to trim, and you can then continue with trimming if you want. Now let's go back to extrapolate. Fine. Then go to desmear, and we can do 5 iterations. Maybe even one more, and we're done. I think this is fine. You can already see how in this range the data points are starting to be very jumpy. As you keep desmearing, you will be improving and improving, but eventually you're gonna run into troubles with generating more and more noise in the area where the input data were noisier. Okay, and then I'm gonna do a save. So now if I go in plotting tool, for example, and I pick that I had some desmear test here. If the Irena finds that it has slit smear data only, it will put the slit smear data in there. So if you try to plot desmear test 3, you just get a slit smear data. But I believe we desmeared 4 if I'm not mistaken. If you add it in there, if the Irena finds a desmeared data also in the same folder, it prefers the desmeared data, so now you will get the desmeared data. You can also add the slit smear data in there if you want, and when you do that you will then get both. So now the green curve is the desmear test 4, that's the original slit smear data. You can see they were different from the desmear test 3. I don't even know what the data were, but you can see that was what we had there. When we desmear it, we gained, and you can see that in this range you gain 2 decades in intensity. Of course, as the data merge at high angles, you will not have any difference between them. So the total dynamic range, the total intensity range of the instrument is the equivalent pinhole equivalent is higher for slit smeared instruments. Now, if you're using Irena, and you plan to use only Irena in Igor Pro, then you should not desmear the data. There is really no reason to do that, because Irena has slit smearing built in the modeling. It will figure out that you have a USAXS data, slit smeared USAXS data, if they came from the USAXS instrument, and it slit smears the model. So you get the same results if you do fitting to slit smeared or desmeared data. You just don't have to desmear them. And the desmeared data, as you can see, there is an increase in noise. So for example, in this range, if you look on the green curve, that's the input curve, it was less noisy than the desmeared curve. That is a standard problem of desmearing. As a colleague of mine says, desmearing makes mountain out of a molehill. And so you really want to have as little moleholes going in there as possible. Anyway, so I think that's all. This is a relatively straightforward procedure. The critical parts are to keep in mind that you have to trim off any and all garbage points which, you know, have a high noise. They'll be impossible to desmear. So throw those away. Keep in mind that smooth small angle scattering data desmear actually quite well. Where you have a problem with desmearing actually happens if you are trying to desmear data which have diffraction peaks. If you have diffraction peaks, their desmearing really doesn't work very well. And that's it. If you have any questions, there's a manual, and there is a and there's always a chance to send me an email and talk to me. Okay.